Alright, so here we are going to be looking at using trigonometry to find angles of right triangles. In addition, we're going to be looking at some problems where we might have to find an angle, we might have to find a side, and we're going to have to decide on the most appropriate method for doing that. As before, make sure we're in degrees mode. Make sure your calculator has a little D or you might say DEG, depending on the model of your calculator. We have these three formulae that are given to us on our provincial exam formula sheet, and so we will always have access to. However, you may prefer remembering SOHCAHTOA as a quick way to remember these ratios, and that's really up to you. Now, typically any basic trigonometry problem has four main steps. We're gonna make sure we got a diagram of some sort with a right angle triangle in it. We're gonna label each side in that triangle, opposite, adjacent, and hypotenuse. We gotta choose between our trig ratios, sine, cosine, or tan, based on which sides we are comparing. And then lastly, we're gonna use our algebra skills to solve for an unknown variable. All right, so let's look at question 1a. We are looking to find this unknown angle here. We've labeled it with a Greek letter T for theta, and that's just traditional. If you prefer to write an X in place of it, that's just fine. It really is just a symbol representing the fact that we don't know how big it is, but we want to know. All right, so well, that's a little different than what we did before on 8.3, but that's really the only difference, is that we're looking for an angle rather than a side. So we're going to continue on as if there's nothing really different about this. So first I'm going to say, okay, well, which is opposite? Well, it's this guy over here. I'm going to label it just O. Adjacent is the side that is next to theta, and 24 kilometers alongside is our hypotenuse. And I say, well, which two sides are we comparing? Well, it looks like we're comparing the adjacent to the hypotenuse. All right, so that means I'm going to use my cosine ratio because it compares adjacent and hypotenuses. All right, I'm going to write that out. Cosine of my Greek letter T, my theta, is equal to my adjacent 18 kilometers over my hypotenuse 24. And for all intents and purposes, I'm going to ignore my units. Now, it's not just because in some previous questions we might take out the units and put them back later, but rather it turns out it doesn't actually matter if these are kilometers or meters, as long as we have a triangle with these dimensions, this ratio, adjacent and hypotenuse, the angle is actually going to be the same, even if this was 18 millimeters and 24 millimeters. So in this case, we say the units cancel out if I included my units here and here. And that is a consideration you might want to be thinking about if you're planning on going on to Chemistry 11 or Physics 11 next year. Other than that, it may be just an interesting curiosity to you that you get to forget if you choose. All right, anyway. Back to the question. We're trying to find this theta, this unknown, and we got to do the opposite operation that's being performed. And right now, there's this operation cosine, and it actually kind of looks like it says cosine times theta. So you might think you divide by cosine, but that is not, in fact, the case. Cosine is not being multiplied by theta, but rather it's performing an operation on theta, in the same way that a square root sign might be performing an operation, asking what is the square root of something. And so if I had the question, square root of theta is equal to 18 over 24, well, you would definitely not think we divide by square root to do the opposite. In fact, we would square both sides. Squaring is the opposite of square rooting. And they actually end up canceling out. So the question really becomes, well, what's the opposite of cosine? Well, if we look on our calculator, we see right above the cosine button, there is a cosine -1, which is defined to be the inverse of cosine. And you might notice there's a bit of a pattern on calculators, sometimes depending on the model. Like say the opposite of x to the power of 3 cubing something. Oh, we got a little cube root function as a second function. And actually, there are some other instances of this, four functions that we haven't learned yet, and you might learn maybe if you go on to pre-calculus 12. Anyhow, so the opposite of cosine is cos -1. So that's what we're going to do to both sides of the equation. Cosine -1 of cosine theta. All right, and that's going to be equal to cosine -1 because we have to do the same thing to the left that we do to the right. That's our only algebra rule that we have to observe. And if we do one thing and then it's defined opposite, always it cancels. That's actually why we do the opposite, so that we can undo it and cancel it out. And it leaves us just with a theta is equal to cosine -1 of 18 over 24. All right, so how big is that? Well, let's just check. I press the shift button to access my cosine -1 or inverse cosine function. Open up a set of brackets, 18 over 24. I can do the fraction button if I want, or I can do division. Doesn't really matter as long as I'm in brackets. And it says 41.409, but I'm asked to round to the nearest tenth. So that means I'm going to write down 41.4 degrees. Of course, the units are degrees here because we have been finding an angle. All right, 41.4 degrees. All right, moving on. Part B. So again, we're going to label up this triangle. This guy is the opposite. I'm going to label it OPP this time. Hypotenuse is the long guy here, HYP. And the adjacent is the unlabeled side here. All right, looks like we are comparing opposites and hypotenuses. So which trig ratio does that? Well, it turns out it is the sine function. Okay, so I'm going to rewrite that. I'll write it out. Sine, and inside the angle, well, I've got this Greek letter, t, theta. That's equal to 56 nanometers over 80 nanometers. All right, great. So I need to isolate theta, and I'm going to do the opposite of the operation sine. And as we saw before, there is an inverse sine function, which is written sine -1, and that undoes the operation of sine. So I'm going to do that to both sides of the equation, sine -1 of 56 over 80. Great. These guys end up canceling out, and we're left with just a theta, and that's equal to the inverse sine of 56 over 80. All right. And so we use a calculator, inverse sine of 56 over 80. I'll use division this time just to demonstrate we could use either. And we get 44.4 degrees. Great. Theta equals 44.4 degrees. Not so bad. All right, moving on. So question C asks for the angles defined relative to this angle theta. Okay, so this one is adjacent. I think you'll agree, and this one is the opposite, and hypotenuse here. We're comparing opposites and adjacents. So that's going to mean we're going to use tan of our angle theta. Okay, and that's equal to the opposite 16 over the adjacent 16. Interesting, the two sides have the same length. I'm actually going to add a little line here, or two lines, on both sides, and that's a way in geometry we have of indicating two sides have the same length. I'm going to come back to why I do that. Okay, so obviously, if you followed A and B, you're going to know that to do the opposite of tan, we're going to tan -1, or inverse tan, both sides of the equation. All right, and that's equal to tan -1. But rather than write 16 over 16, I happen to recognize that that really will simplify to the value 1. 16 divided by 16 is 1. Any number divided by itself is just 1. All right, and so we go back and we say, okay, these cancel out. I left with my theta, and over on the right-hand side, I get tan -1 of the value 1. All right, so how big is tan -1 of 1? Shift tan 1. It's 45. My calculator seems to be in an interesting mode, which adds a bunch of extra decimals, even if a number doesn't necessarily need it. I'm going to fix that in a second, but really this is a funny way of writing the number 45. Okay, so it says that the angle theta is 45 degrees. Okay, now looking back at this diagram, could we have reasoned that that angle is 45 degrees in any other way without using trigonometry? And the answer is yes, we definitely could. So if we look, we say, okay, well, this is 90 degrees here. We know that for sure. And we know that this is a triangle with two sides that are equal. We have a word for that. That is a isosceles triangle. All right. And so an isosceles triangle means that it has two sides that have the same length and two angles, opposite angles that have the same measure. So that means this is an angle of size theta as well. Okay, so if that's 90 degrees, and if I know a triangle has angles that all add to 180 degrees, that means I could say 180 degrees must be 90 degrees plus theta plus theta. Okay, so that actually might be quite a simple algebra question to solve. I could subtract 90 from both sides, 90 degrees that is, and 180 take away 90, that's actually 90 degrees. And I can group these like terms, a theta plus another theta, that must be two thetas. And I would isolate theta by dividing by 2, dividing by 2. Oh, what do you know? I find that theta is 45 degrees, and I could do that actually without trigonometry. Interesting. It's good to know that our methods can be consistent. We can use two different ways to find the same value. All right. Now, if you got an earlier version of this worksheet, you may have these two values inverted, and that is actually an impossible situation. The hypotenuse always has to be the longest side. The side opposite the right angle always has to be longest. So if this was 4 miles and this is 6 miles, and you try and solve that trigonometry problem, your calculator is going to say that you are talking about an impossible triangle. So I hope if you are watching this video that you can just adjust that. Maybe you're watching this video because you found that error and you're confused about why your calculator says you're wrong. Okay. So with this adjusted, I'll just label up my triangle, and it says adjacent over here. This must be opposite. Hypotenuse, we're comparing opposites and hypotenuses, so I'm going to use sine. Sine of theta, my unknown, is equal to 4 miles over 6 miles, or 4 over 6. All right, I'm going to do the opposite operation to both sides, so sine -1 of sine theta, and it's equal to sine, oops, close the extra bracket, -1 of 4/6. All right, sine -1, inverse sine I should say, and sine cancel out, leaving us with just a theta, and that's equal to sine, pardon me, inverse sine of 4/6. All right, so inverse sine of 4 divided by 6 says it's 41.8. Theta equals 41.8 degrees. Okay, I'll put a little box around that and around this guy. Great, moving on. Okay. Okay, so question 2 says find the unknown side or angle. Actually, we're not sure which variable we're going to need to solve for. We may need to use all of our different trigonometry tricks. By now we found there are actually 3 different situations for basic trigonometry problems. 2 involve unknown sides, an easy situation and a hard one. We'll see all 3. And the other one is finding an angle, which we just were mastering. All right. Again, we're going to round our answers to 1 decimal place. Okay. Well, let's look at A. All right, A, I'm going to label these up quickly now because I think you guys are probably getting the hang of this. All right, that means you're going to use a cosine ratio to compare adjacents and hypotenuses. So I, again, start by just writing that out. Cosine of 78 degrees must be equal to x, my unknown, over 11 millimeters. I'm just going to write it as 11. And to do the opposite of dividing by 11, I got to multiply by 11 on both sides of the equation. Those cancel out, and I get x is equal to 11 cosine 78. Okay, so 11 cosine 78 must be equal to 2.3, rounding up, millimeters. 2.3 millimeters. And that's equal to x. All right. Moving on to question B. Again, I'm going to label up, that'll be my opposite here, my adjacent, and my hypotenuse. And it looks like we're comparing opposites and adjacents this time, and that's TOA. We're going to use a tan function. It's going to be tan theta. And it's going to be equal to 6 feet over 18 feet. All right, looks like our variable this time is our unknown angle. All right, so we're going to isolate that by doing the opposite of tan to both sides. So we're going to do tan -1, or our inverse tan, to both sides. And that's equal to tan -1 of 6/18. All right. Let's cancel out. We end up with theta is equal to the inverse tan of 6/8. Oops, 6/18, I believe. That gets 18.4 degrees. All right. Moving on, let's take a look at question C. C, we'll just label this up. That is opposite, that is adjacent, that is hypotenuse. We're comparing opposites and adjacents again. Okay, so that means we're going to look at the tan ratio, tan of 41 degrees, and that's equal to 540 meters. Our opposite divided by our hypotenuse, x. Probably shouldn't include the meters there, that'll just get confusing. Okay, this is our trickier algebra situation. We have a variable in the denominator. We need to get it out of the denominator before we start using our regular algebra rules. Now, general rule of thumb is we're going to want to get rid of denominator, so I'm going to multiply both sides by x. That's going to undo dividing by x. All right, that leaves us with an x times tan 41, and that's equal to 540. All right, and lastly, that means I still need to isolate x. It's being multiplied by tan 41, so I'm going to divide by tan 41. Divide by tan 41, cancel, cancel, and I end up with x is equal to whatever 540 divided by tan 41 is, which is equal to 540 divided by tan 41, 621.2. 621.2, and the units are meters. Moving on to part D. Alright, 2D. Again, we'll label as opposite. This looks like the hypotenuse, that's adjacent here. Alright, looks like we're comparing opposites and hypotenuses. We're going to use sine of my angle 51 degrees. It's equal to my opposite, x, over my hypotenuse, 57. Looks like a pretty simple algebra situation. I got to multiply by 57 to undo dividing by 57. So those cancel out and I end up with x is equal to 57 times sine 51. 57 sine 51 is 44.3 centimeters. Okay. All right, and then we have a new triangle here. We've got to label this up. That's the opposite over here. 4 light years is our adjacent, is next to the angle, and the hypotenuse, the longest side, is 5. All right, and then we're going to look to see which ratio we're going to use, and it looks like we're comparing adjacents and hypotenuses, so we're going to use cosine. Cosine of our unknown theta, well, it must be 4 light years over 5 light years, but it might as well be 4 centimeters over 5 centimeters, because those units end up canceling out anyway. All right, opposite of cosining an angle is to do the inverse cosine. So we're going to do that to both sides. Cosine theta, that's equal to cosine -1 of 4/5. All right, those cancel out. We get theta is equal to whatever the cosine -1 inverse cosine, or arc cosine if you prefer, of 4 divided by 5 is. That's 36.9. Oh yeah, I should have known that. It's a 3, 4, 5 triangle. This is not to scale. All right, 36.9 degrees. Great. Moving on to question F. It looks like this guy's the opposite. This is the hypotenuse, and that's the adjacent here. Looks like we're comparing adjacents and hypotenuses, which means we're going to be looking at a cosine situation. So I'm going to write cosine of my angle 70 degrees is equal to adjacent, which is 3 millimeters, over my hypotenuse, which is x. All right, we've seen this before. To get rid of a variable on the bottom of a fraction, we want to start by multiplying both sides by x. Let's cancel out, and we end up with 3 is equal to x times cosine 70 degrees. Now we want to undo this multiply by cos 70, so we're going to divide by cosine 70, divide by cosine 70, and it's going to equal x is equal to whatever 3 divided by cosine 70 is. 3 divided by cosine 70 is 8.8. 8.8 millimeters. Great. All right. So next we move on to some situations where we have to read a passage. We have to grab the important information out of it. Maybe we draw a diagram now, which we haven't needed to do before, and then solve a trigonometry problem. All right. So what do we got here? Mr. Norrish wants to determine if a vertical cliff, okay, I'm going to highlight that, that's important, it's vertical. Vertical, maybe if I see the word vertical, I might draw a little symbol to remind myself that vertical means straight up and down. Okay, vertical cliff is short enough for him to rappel down with 30 meters of rope. So I guess the question is the vertical cliff longer than or shorter than 30 meters? Shorter than 30 meters, he should be able to rappel down. All right, so let's read on. He paces out 20 meters away from the base of the cliff. Okay, so let's go slow through that. We're talking about the base of a cliff. All right. And he's going to be 20 meters away from that base of the cliff. Okay, that sentence is almost written backwards in a way. The important information is we started from the base of the cliff, and then we walked 20 meters away. Okay, I feel like that might be enough information to maybe start sketching out what I've got so that I don't forget. Okay, so we've got some vertical cliff, so I'll draw that as a vertical line. And it looks like we want to know how long it is. We're not going to label it 30 meters because we don't actually know if it's 30 meters. We want to know if it's less than 30 meters. Okay, so I'm just going to write, maybe a question mark isn't great. Maybe I'll just write X. X, unknown cliff height. Okay. And he walks 20 meters away from the base of the cliff. Base means bottom. Okay, so this is the base of the cliff, and I can imagine there's a ground here. He's going to walk 20 meters away. So that's going to be out in this direction. Now, you might have drawn that out to the right. You might have pictured the cliff off to the left. That is irrelevant. You can do either. It should be totally fine. All right, so that's 20 meters, say. Now, I don't know how to draw that to scale relative to this side because I don't know how long that side is. So I'm not going to concern myself with this diagram being to scale. Now, I also know one other thing. I know that these two will meet at a 90-degree angle, or at least I can assume that. It doesn't mention anything about the ground not being flat, so I should assume the ground is flat. Okay, moving on. Okay, base of the cliff, and from there he uses his phone to measure out the angle of elevation to the cliff. Okay, angle of elevation, that's a vocabulary word. Angle of elevation. So, angle of elevation means if we have an imaginary horizontal line and your eye is at the base of it, I use the word base, I probably should use just the word end. So say you're looking up at something because it's elevated. So you have a line of sight and you have elevated it up from looking horizontal, and this is an angle of elevation. If you were looking downward, say, that would be an angle of depression. Both are measured against a horizontal line, an imaginary one. Okay. So that means if he walks out 20 meters, uses his phone to measure the angle of elevation to the cliff. So we imagine an imaginary line looking up at the top of the cliff. And then we end up with a right angle triangle. Okay, that's pleasing. And we know the angle of elevation. Okay, he finds the angle of elevation to be 60 degrees. I'm going to highlight that as well. Angle of elevation, 60 degrees. That means angle upward from a horizontal line was 60 degrees. And the question is, does he have enough rope to rappel down the cliff? In other words, if he has 30 meters of rope, can he get down this cliff all the way or not? Okay, so to answer that, I guess we should start by, well, now that we've got a diagram, we'll label up our triangle. This is the opposite here, the adjacent here, and the hypotenuse, and we want to know what the opposite is, and we know the adjacent. O and A, you're probably getting the hang of this by now, that we're looking for a tan ratio in this case. So tan of 60 degrees is equal to my opposite X over my adjacent 20. Okay. This looks pretty easy to solve. This is my easy situation. I'm going to multiply by 20 on both sides of the equation, and I end up with 20 times tan 60 degrees. That's equal to my value x. And if I put in my calculator, 20 times tan 60, looks like the cliff is 34.6 meters. Okay, so of course we weren't actually asked how tall the cliff was. We were asked, does Mr. Norrish have enough rope to rappel down the cliff? And we look back and we say, well, he has 30 meters of rope to rappel down. Does he have enough? No, because the cliff is 34.6 meters tall. So we could say, no, Mr. Norrish does not have enough rope. If he tries to rappel down that cliff, he will be 4.6 meters short, which is about 15 feet. He might survive it, but I don't think we should test it. All right, great. It's good practice if you're answering a word problem to answer in words your answer. All right, moving on. Okay, let's take a look here. We got a situation. Caden has a 13-meter ladder. He wants to place it against a wall. So he will leave 5 meters between the ladder and the wall. Okay, I'll get my highlighter out. Caden has a 13-meter ladder. Okay, 13 meters. He wants to place it against a wall. Okay, so I can picture the orientation of a wall. It's probably vertical as well. It doesn't say that, but we can assume it, unless we're told otherwise. So I'm going to write a little symbol for vertical. And so he will leave 5 meters between the ladder and the wall. So I'll highlight that whole clause. 5 meters between the ladder and the wall. Okay, now I didn't actually highlight the question in question 3, what we were being asked, but I will here. It's a good habit. At what angle will the ladder be placed against the wall? So, okay, at what angle will the ladder be placed against the wall? Okay, so maybe we should start sketching this out. So, okay, what do we have? A ladder, a wall. I can picture a ladder being placed against a wall, and it looks something like this. A wall would be vertical, and it doesn't say how tall the wall is, okay, so we can assume it's longer than 13 meters, I guess, and I can picture a ladder being placed against it. All right, and I guess I could probably fill in the gaps here. I know that the ground would be along here somewhere, and that these would meet at 90-degree angles. I know the ladder is 13 meters long, so I should label that. And I can see that Caden wants to leave 5 meters between the ladder and the wall. Now I can infer that that means along the ground, because obviously it's not up here because the ladder has to touch the wall. So I can assume that this distance here is 5 meters. And the question asks, at what angle will the ladder be placed against the wall? Okay, so we're looking for an angle between the ladder here and the wall itself. That's what that question really asks. So we'll look for this angle theta. Now, you know what, we've been using a lot of thetas, but actually I think I'll just use the letter x, just to demonstrate that we can use really any symbol, theta, x, whatever, for an angle. Theta is just traditional, and I just want to make sure you guys have seen that before. All right, so got a diagram that looks just fine. Now we can start by labeling up our triangle. That means 5 is our opposite, our value of x. 13 is our hypotenuse. And if I wanted to, I could not even label that. I know that I'm comparing opposites and hypotenuses, so which means I know that I'm going to be using my sine ratio. That means sine of my unknown value x, that's equal to 5 meters over the 13 meters. All right, my opposite of sine ratio is the inverse or arcsine. Sine -1, or arcsine of sine x, is equal to the arcsine of 5/13. These cancel out. I get x is equal to whatever my inverse sine of 5/13 is. Okay, inverse sine of 5/13. Looks like it's 22.6 degrees. So angle X is 22.6 degrees. And again, to answer this question in a sentence, I would say the ladder will be placed at an angle of 22.6 degrees against the wall. It's important to add this against the wall part to contextualize 22.6 degrees, so we know that it's not this angle down here. Oops. All right, grand. So last question, question 5. So what does it say? What is the length of the largest rectangle? Has a width of 8.5 inches that you could cut from a circular piece of cardboard that has a diameter of 30 inches. Okay. Now, I happen to know this is actually quite a tough problem, not undoable, but you should know this is, I would say, a bit of a challenge to unpack all this information. All right. So luckily we're given a diagram, and I think you would probably agree that this would be the largest rectangle. That would be 8.5 inches wide. And I guess, what else do we know? We know it's got a diameter of 30 inches, so that's actually supplied for us here as well. Okay, that's the diameter. Diameter means the distance across a circle, as long as you go through the center, that is. All right, and where is the question here? The question is actually here. What is the length of the largest rectangle that has these constraints? Okay. So what can we do here? So the important part about this question, the real crux, is to recognize that the diameter of a circle is the same in all directions. So it's 30 inches along this axis down here, as long as we go through the center of the circle. It's 30 inches along here. It's 30 inches totally horizontally here, but none of those values really help us, except for if we tilt that diameter and have it go across the center of the circle here. Okay, and we know that is the diameter as well, and that would be 30 inches long. Okay, now if we can determine that, then it looks like what we've created out of this large rectangle is a right angle triangle. All right, and if we want to know the length of this side, well, if we're trying to find a side of a right angle triangle, we could use trigonometry if we wanted, but actually we know a more elementary way to do that. We can use the Pythagorean theorem. We know that the relationship between the square of each of these legs of the right triangle is equal to the square of the hypotenuse. So I can just write out the Pythagorean theorem. A squared plus b squared is equal to c squared. And maybe I'll label them. I'll call that A, put a circle around it. I'll call that B. I'll call that C. Okay. And that means, I guess A is my value x, so I'll replace it with x squared. And B is my value 8.5 inches, so I'll call that 8.5 squared. And C is 30 inches, so I'll call it 30 squared. Okay, so maybe I should simplify before I do any algebra steps. 8.5 squared is 72.25. All right, so 72.25, and that's equal to 300 squared. That's 30 times 30. Which I happen to know is 3 times 3, or 9, plus these extra zeros, so it's 900. To find x, I'm going to get rid of this squared and this plus 72.25. I have to get rid of the furthest thing away first. I'm going to subtract 72.25 from both sides of the equation. 72.25. They cancel out. I end up with x squared is equal to 900, take away the 72.25, 827.75. All right. Now I need to get rid of this squared. Well, we talked earlier about how the opposite of squaring is square rooting, and vice versa. Okay, so I'm going to square root both sides to undo that operation, and that gives me x is the square root of 827.75. Now, this calculator doesn't require me to type that in twice. It actually says if you have this value of 827.75, you can just press the square root button and equals. It does it for you. All right, so that just tells me that the length of A must be 28.8 inches if I round it to one decimal. All right, and lastly, a good habit is to write out the answer in words. So the length of the largest rectangle is 28.8 inches. There is my answer.